Good morning, everybody, or good afternoon, depending on where you are. Welcome to the Understanding Welding Equipment webinar presentation today, brought to you by the Industrial Fabrics Association International, specifically the Equipment Division. My name's Jonathan Palmer. I'm the president and owner of Autometrics, so I'm going to be moderating today's webinar. I'm the vice chair of the Equipment Division. Before we get started, I do want to give everybody just a few pieces of information about how to participate in today's webinar, in case you haven't been on one of these before. We're going to go through our presenters. Along the way, if you have questions, please feel free to submit those questions. And the way to do that is just by typing. So you should see a control panel, probably on the right side of your screen. And in there is a little area for questions. So in there, you get to type your question and submit that. I'll be keeping track of those, and we'll get to those questions as we near the end of our presentation, and make sure that as many of those as possible get answered. The PDF of today's presentation is available for download already. It should be under the handout section of that control panel. As well, there's going to be a link to download this presentation emailed out to all of the attendees later on in the week. So to get started, I want to introduce the presenters we'll have today. We're going to have Jason Damas from Miller Weldmaster, Ken Huber from Leister Technologies, Tracy Eveling from JTE Machines. So Tracy is going to start us off today, and at this point, we're going to go ahead and hand this over to her and get going.
Thanks, Jonathan, and thanks to the IFAI staff for doing a great job organizing this webinar. And thanks to you all out there taking time off your busy day, and some of you during your lunch hour to join us. Okay, I am Tracy Eveling, as Jonathan said, co-owner of JTE Machines, and we're an automation solution supplier and service provider for both cutting and welding industrial fabric solutions. And we also are the exclusive distributor for Fiat Machines. Okay, and here's the story behind the picture on the right. Just about 20 years ago, I was pretty much in the same boat you are today, curious and wondering about welding industrial fabrics. Actually, I never really even heard about heat welding materials, having joined the industry mid-career. In fact, the only experience I had melting plastics was melting the sequins off my majorette uniform twirling fire back in the day. And there you go. There's a story on the right. Maybe a little bit TMI, but at least now you know a little bit more about me. And let's get on to some real learning. So, why do we call it high frequency? And is it the same as radio frequency? Well, yes, HF and RF are interchangeable. They're the same thing. It's just that HF is referred to as the high frequency in Europe, and RF is really more commonly used in the States. RF welding involves an electromagnetic wave that excites short chain molecules found in PVC, polyurethane, and a few other plastic materials, as you see below. And it creates the heat from the oscillation of those molecules. And under cool pressure, those molecules fuse to create a weld that is better than the one-ply material itself. The tool on an HF or RF machine is simply providing a path for the energy. And it's not the thing that gets heated up, but it actually may get hot from the heat of the material reaction. So something good to remember, though, about RF tools are that they are very quick and easy to change in and out, and they're relatively inexpensive. So you could be doing a high variety of tasks with the one machine. Here you see a list of materials that are naturally reactive to RF or HF, and you'll see that I actually did include a PVC composite, which refers to new materials now. There's new technical materials coming out every day, and some, like the Natura from Herculite, are actually very cloth-like in the touch and the hand, and they're actually used for in place of an acrylic, for example. They are completely RF weldable, so don't be fooled that you have to see some kind of shiny material to do RF welding. How does it work? The radio frequencies is, no kidding, an available frequency on a CB radio channel between channel 13 and 14. The RF generators used in welding fabric are usually 27.12 megahertz, which means that the molecules are spinning 27 million times a second. Very fast. The weld starts from the middle rather than the surface, and as such, it results in a weld that is hermetic, efficient, and consistent throughout, and a process that does not emit gases. So the takeaway from this slide, you can use as a reference, it's the most important thing to remember, though, is that the more sophisticated the technology, the less skill that's required by an operator to make your product perfect each and every time. Why and when should we consider using RF welding in the fabrication process? Well, why? Because it is actually one of the easiest ways to weld your materials with no experience required. But more importantly, when? What are the products that are commonly welded with RF? Well, as you can see here, there's a very extensive list, and this is really just the tip of the iceberg. Because RF penetrates multiple layers, one cycle can weld, for example, an apex of a tent, or webbing on a hem, or a clear window with hook and loop attached to it at the same time in one hit. Or, as you can see here, the perimeter and valve of a medical bag at the same time. It's just a matter of having the right tool and pressing a single button for most of these products. So the range is pretty broad. You've got small products like the medical bag on up to huge, large format products like the inflatable building, and you've even got the 3D products like you see here, the rooftop accessory that is a 3D type of weld. So there are many different forms of RF machines. You may be most familiar with the bulky C-frame types that are out there, that you have the two people on each side pressing two buttons each at the same time for the upper platen to drop, and then they have to go into the weld cycle and remember not to touch the table because they might get burnt. Well, that was then, and this is now, and today the newer machines are much different and have better shielding than ever before. And this makes them very safe, and they also have advanced features such as inching, auto-tuning, PLC controlled touchscreens, and they require very little skill to operate. All this is possible because of the advancements in shielding. You can have a computer right there on board. So most RF machines are rated on how much kW of power they produce. The range actually could go from 1 kW to 200 kW. But when you're considering RF machine, it's better to ask, what is the total weld area capable of this machine, rather than what is the kW rating, because this average can vary almost 40%. For example, the average older machine welds 4 square inches per kW, and the newer machines can weld up to 6 square inches. On the top row, you see a double welder. This is a double station, one generator, rather small footprint RF welder, and this is commonly used in testing and small format. On one side, you can actually be bar welding, and on the other side, you can actually have a shape tool or several shape tools, and the computer keeps track of the recipes for either side. The next one is a transportable RF welder. It actually can be rolled around the production floor on wheels, and it's fairly unique because most of the machines out there, the older machines, are actually too heavy to do this. So this is a lightweight transportable RF welder. And to the right on the top is a fairly unique setup. It is a stationary machine with an integrated moving table that enables accurate and easy setup for products ranging from zippers on roll-up screens to dock seals, again, with very little skill required and high versatility. So below you see much larger format RF welders. The one on the left is a double-sided shuttle, high-powered, and it's actually welding G-suits in one hit. So that's about a 15-second cycle time for one whole product. Then the turntable on the right is unique in the fact that it has two different generators or welders attached to one turntable. And this machine could be welding medical bags, and then in another facility, it's actually welding the flashings of the rooftop that we saw earlier. So as you can see, there's lots of versatility built in, and there's lots of different formats of RF welders. There's even more. These are examples of traveling head RF welders. And you may be familiar with the blue color and the long tables associated with these machines. So these machines help to weld applications such as billboards, large tensile structures, liners, and tents. And they actually help to automate the repetitive process of welding one weld after another down a 200 length table. It's a great help in material handling, and it allows the operator to focus only on the setup, while at the same time the welder works independently and automatically. On the left, you see a traditional style traveling head. On the top right, you see actually a remote control turning head machine. And then below, you actually see a turning head on a long table. So let's move on to the other technology that I'm going to talk about, and that is ultrasonic. So many people think that ultrasonic and RF are the same thing, that it's interchangeable. I hear this a lot. And actually, they're not. Ultrasonic is basically a sound wave, and it actually is a sound wave at a high frequency, but much lower than RF. It's only about 15 kilohertz to 40 kilohertz rather than the megahertz, 27 megahertz that I mentioned earlier. When your applications involve materials and perhaps you need to weld variable curves and your materials are like thermoplastics, that's when you should consider ultrasonic. It's great for polyesters, polypropylenes, polyethylenes, Tyvek, polyurethane foam, and medical products. I did include acrylic on there because many people are actually using ultrasonic with tape to weld their acrylic products. And this is, again, a review of how it works. It's actually a vibration of the metals around the fabric that causes the fabric to melt and then fuse, rather than the molecules in the material itself oscillating. So it's a mechanical motion that bonds the material, and the material forms a molecular bond, but only after being reacted to by the metal that's vibrating around it. And those two metal pieces are often referred to as the horn and the anvil. It's fast, it's clean, it's repeatable, but really it's better for small areas. It gets very expensive when you try to extend it to large areas. There's usually no tape or adhesive necessary, especially with the polyethylenes and polypropylenes. And there's no fumes when burning the material when welding the material. And the tools do not get hot to the touch. This slide shows some applications using ultrasonic. Believe it or not, the picture on the left includes both an RF and an ultrasonic weld. It's very hard to tell the difference. We actually developed a machine that closes pockets on shades, for example. It's a 2-inch weld. It's very efficient using the ultrasonic machine. But you can also consider other products that are welded. Polyester flags, for example. Even a polyurethane foam koozie can be welded in one hit using ultrasonics. And then to the right, you see a bulletproof vest. And this is actually a product being made by a rotary ultrasonic machine. Other items you can see here, again, this is just the tip of the iceberg of different products that are using ultrasonic today. So these are some examples of RF welding equipment used in industrial fabrics. The machine on the left is actually a cutting system. Because we have a little bit of core competency in cutting and welding, we actually developed a XY cutting system that you load the pattern into. It actually cuts around the pattern, and at the same time, it's welding or serging the edges. And this is being used, for example, in an extreme sleeping bag application where they needed to serge their batting in nylon material prior to taking it to the sewing station. On the middle top, you see our handheld, and that is, again, very handy in tacking, small format welding, and everything in between. On the right is the sonic bar welder, which is, again, fairly unique, but here you can weld about 11 inches, and that's about the max of a reasonably priced generator that you can weld 11 by ½ inch. And then on the bottom, that is the example of the machine welding the bulletproof vest. It's actually welding and cutting at the same time, much like a sewing machine, but with very little skill needed and, of course, no thread. Let's move on to the third technology that I'll be talking about today, and that is PTFE or ETFE welding. Well, what is it? Well, PTFE and ETFE, as you know, are materials that are actually becoming more and more in demand. And with this expanded use of this highly durable, heat-resistant material, you would think that any kind of heat welding would be contradictory to what the material was engineered for in the first place, which was heat resistance. Well, there is a way, and in the past, only sewing was used, but now there's a commercially available machine that uses very high temperature with direct heat and alternating cold pressure to bond the PTFE and ETFE materials. The operating temperature of this welder is about 600 degrees Fahrenheit, and the cycle times are actually pretty production worthy. So within about a minute or two, you can actually move through your large format Teflon paneling project at 1 meter hits and really get out there on the production curve in terms of utilizing this machine instead of sewing. The other benefit is that it results in actually a very smooth surface, and it can withstand high tension. Containment systems, roof membranes, shade sails, stadium covers, semi-permanent structures are all weldable using an ETFE or PTFE welder. And on the left, on this slide, you'll see an ETFE material. That is usually more translucent materials. And on the right is more traditional PTFE or Teflon materials. And below that is a close-up of that material actually getting welded. And here's the machine. It's a gantry-style machine with a Z-cut and the alternating head applying the high heat and extreme cooled pressure to solidify those molecules and fuse together the material. And this actually runs along a track on the floor, and at the moment there's actually enhancements underway to improve the automation capabilities of this process. Speaking of automation, your return on investment for these machines is very important, and that's probably one of the reasons why you're here today, is what's it going to cost me, and am I ever going to see a return on my investment? Well, for many of the machines that we discussed here, there's several factors that go into your return. Obviously, labor is one of them, but because you achieve a hermetic, very flat, very almost invisible seam, your quality of your product goes way up. there's no puncturing of the material. There's very little edges or ridges with special tooling that can be used, and it's highly efficient. You're using less energy, you're doing less process, less trimming, so all of that adds up to savings. And usually that savings is paid back, or you can pay back an investment in about 6 months to a year on most investments. And here is an actual example, albeit it is somewhat of an extreme example because we're talking about an automated building production process. You've probably seen the large structures that are air inflated. Well, in a current scenario, they're actually using older RF welders, and they're using about 10 operators, 2 per machine, but they're only achieving 20 cycles per hour. And this is mostly due to the material handling involved to folding, refolding, moving the material to the machine, going through a 36-inch cycle, and then doing it all over again. So all of that wait time and all of that loss of productivity adds up to only about 60 feet per hour. So let's say they pay a loaded cost of $20 per hour to each employee. That's about $1,600 per shift for 480 feet. The labor cost per foot is $3.30. Well, if we come in there with just one traveling head, long welder on a 200-foot table, you're going to actually achieve 180 cycles per hour. Why? Because once you've got that material on the table, you really don't have to touch it. And the other reason is that the machine is actually welding while they're setting up for the next couple welds. So you've got 900 feet per hour at a total of 3 people at the most. That's 7,200 feet per shift and $480. You can see the math here is pretty significant. Your savings overall, you could be saving millions in the end if you're going to be doing that much output, and obviously you can pay back this investment in way less than a month. So that concludes my overview of RF, ultrasonic, and PTFE welders. You can visit the JT Machine YouTube channel by clicking the top link on our homepage if you'd like to see this technology in action. And now back to Jonathan to introduce our next presenter.
Thanks, Tracy. Just a reminder to everybody, if you've got questions, you don't need to save those to the end. You can go ahead and be typing those into the question box so we can kind of know what's coming as we get to the end of this webinar today. But for now, let's move to Jason Damas from Miller Weldmaster, and he's going to be discussing the next technologies.
First, I want to thank everybody for joining. And next, I wanted to say that pretty much a weld is a weld is a weld. It's our job, Tracy, Ken, and I, to describe these technologies to help you choose which application of welding works best for your production. A little bit about myself. I've been with Miller Weldmaster for a little over 8 years. I started off building our machines, installing the machines around the world, and now I sell. I'm responsible for the East Coast territory. And I am a Kent State University grad. Go Flashes. So with that being said, let's go to the next slide here. Impulse welding. So what is impulse welding? Impulse welding is, it's about heat, speed, and pressure. You're going to hear me say that over and over during this presentation, heat, speed, and pressure. Impulse welding, in simplistic terms, is a machine. It basically has 2 bars with 2 heating elements on top bar and bottom bar. The heat is created by pulsing energy through the heating elements on the top and bottom of said bars. You control the duration of your welding cycle time with an HMI screen that you can see in the picture there. And then with these machines, you can do hits as long as 20 plus feet, all in one pass. So sizes of the bar vary. And for example of how to do an overlap on a machine, on an impulse machine. You would basically set your bottom panel on the machine on the bottom bar. You would line it up to laser lines, and you would take your top panel, and you could either come from behind or enter this material through the front of the machine. You line everything up as your overlap. Typically, your 25 millimeters, 1 inch. You can go down in size to 8 millimeters, and you would set your cycle time according to the material specific. Push a button, bars come down, and it welds. It fuses or bonds the materials together. Applications for impulse welding can be acrylics, sunbrella materials, awnings with tape, and then your thermoplastic blinds, shades, and screens. It's a very accurate and precise way to weld. It is capable of doing hems, pockets. You can apply zipper, again, acrylics with tape, and that is the impulse. In a nutshell, it's a very precise and simplistic machine to use. Again, you put your materials on the bars, you push a button, the bars come down, they fuse the two materials together. Long straight runs. Next, I'm going to talk about hot wedge welding. Hot wedge welding, again, heat, speed, and pressure is the key to having a successful weld. It's a rotary heating sealing process. Imagine a sewing machine where the material goes through the head of the machine. But in hot wedge welding, you're replacing the needles, the bobbins, the consumables, the threads. No more breaking needles. The hot wedge itself is an aluminum plate that would be heated up with 4 heating elements and a thermocouple, and that's all controlled with an HMI display screen, touch screen. It's a very fast way of welding. So during the welding process, the hot wedge is positioned into the weld rollers or wheels, as you see in this picture here. The material would go on top and below the wedge. So you're actually not welding on the outsides of the materials to go through to bond. You're actually welding on the middle of the materials themselves, the backsides of the materials. It's a very fast, continuous, long, straight runs that you can go through. And the best products that you can do, really any type of thermoplastics, any type of films, thick fabrics, thin films, thick films. It's a quiet work environment. Again, it does long, continuous, very fast, straight seams, primarily your 2D seams. So again, with the wedge welding, you're going to be able to create your hems, your hemming cords, keeters, single-sided keeter, double-sided keeter, pockets, weldable webbing, weld zipper, overlaps, places that you would see that you would use this, companies that would use this, or you're making awnings, truck tarps, pools, liners, tents, shelters, structures, signs, billboards, so on and so forth. Pretty much any type of thermoplastic that you would be looking to weld. And again, just imagine, you're sitting at a sewing machine, but now you don't need the skilled seamstress to do this. You can virtually sit down to this machine and start welding. There is a little bit of a skill, but it's not like your seamstress would have. So moving on, we're going to go talk about an ROI. Actually, here's some examples of machines. So as you can see, the machine on the right, it's a larger machine. It's an industrial machine that would, again, look a lot like a sewing machine head would. And the material, I want you to imagine that material getting pulled through with different types of stepper drives and the wheels engaging, pulling the material through. So your operator would sit in front of the table and have their material, whether they're doing an overlap or perimeter work, and sit down and weld. Machine on the left is a tabletop version. So really, virtually, we can fit any type of size of machine to your facilities. So moving on to the ROI. We have an ROI calculator that we would encourage you to use on any type of capital equipment that you're purchasing for your shop. So feel free to visit the site at any time. There's 3 different tabs that you can choose from. One, you're currently making products and you want to save on your labor and output of production. 2, you're currently buying or importing your products now and want to make it in-house. Or 3, you don't make or buy the product, but you want to start. So the example that I gave, I clicked on you're currently making the product right now. So you would click on the green dot there, and then you would start filling this out. So I took an example of your current production time in pieces. You're making 20. It's currently taking you for one piece to make. It would take you 20 minutes to make it. One employee, $15 an hour, 8 hours per day. You would come down, click next step. You would fill out the next process with either Tracy, myself, or Ken, or whatever type of equipment that you're buying, and you would get the most accurate details you could from that type of machinery in particular. So in this case, your production time for one piece is down to 5 minutes. Everything's the same as employees, $15 an hour, 8 hours a day. Click to the next step. Now you would fill in the price of whatever machine you're buying, whether it's a piece of cutting equipment, a routing table, a printer, whatever that is. You fill out your price. I put $25,000 as an example here, a lease term of 48 months. Click next, and it'll pop up your results. So this is based on labor rate savings alone. So the next slide is going to show you graphs and kind of depict that a little bit better. So labor savings, it's you're saving the same amount of money on the labor, but your production is where the key is here. So if you notice that per day you were making, in an 8-hour shift, you were making roughly 25 pieces a day. With whatever piece of equipment you get, with a welding system that you get, you are going from, the difference of 25 to 95 pieces a day, and then per month, per year. As you can see, that's a major difference with the type of technology. And again, no more consumables. And again, if you guys have any questions, Ken, Tracy, myself, we're all here to answer any type of question for you. We want to fit the best solution to your products that you're making in your facility. And that's all I have for my slide. I'm going to hand it back over to Jonathan, and he can take it from here. Thanks for listening, guys.
All right. I see you guys must be doing a really good job answering questions before they're even asked, because not too many questions yet. But we'll get to those. So last up, we've got Ken Huber from Leicester. He's going to discuss hot air welding. So Ken, go ahead and take it away.
Thanks, Jonathan. My name is Ken Huber. I work at Leicester Technologies as the product specialist for industrial fabrics and technical textiles. I reside in Illinois currently, and I am a graduate of Purdue University. And today I will be speaking on the technology of hot air welding. So what is hot air welding? Well, it's exactly as it sounds. You're using hot air to weld two thermoplastics together, and this is in a numerous amount of applications. Some of the fabrics that can be welded are very common PVC or vinyl, as it's commonly referred to. Other thermoplastics like polyurethane, polyesters, polyethylene, polypropylene. And what can those fabrics be used for? Well, a large amount of applications. Roofing, awnings, signs and banners, geosynthetics, tents, tarps, covers, and especially for hot air welding would be inflatables or complex items, things that are 3D, have curves, that you really can't weld in a straight line. So how does hot air welding work? Well, similar to what Jason had stated, heat, speed, and pressure are the key to welding in almost all these technologies. The heat in this process comes from a heating element in which air is blown over that element and out of a nozzle. That nozzle then focuses that hot air between two layers of material in which want to be welded. This precise heat is then put right between the two layers, and then pressure is added afterwards to make a bond. Now this heat softens the plastic, makes it flow a little bit, and then the pressure bonds them into one fused material. So you basically have a material that is as strong as the original material itself. That heat is controlled in most systems by a thermocouple. That thermocouple monitors the heat and makes sure it stays at the set and desired temperature for the desired material to be welded. So after that heat comes into the spot you need to weld, you need some pressure. You need something to bond that material together. And how that pressure is applied can come in a couple different formats. If it's a hand welder, it would be pressure from a roller. If it's an automatic welder or robot, it would come from the weight of the machine. And if it was a larger rotary welder or stationary welder, it would come from pneumatic pressure. And what's the third component? Speed. So all this happens at some constant continuous speed. And that depends on how fast you'd like to weld. So if you want to go faster, you'll have to increase your temperature and or your pressure to get the same bond as before. Likewise, in the reverse fashion, if you want to slow down a process for whatever reason, you typically need to scale back the heat and the pressure to get those to bond. Now, under all three of these components in hot air welding, you have a continuous welding operation. There's no starting and stopping. You weld till you want the weld to be over. So it really makes for a great process. Now that everyone understands how hot air welders work, I just wanted to go over a few of the different options you have. Starting with the smallest on the left is a standard heat gun, a handheld unit. Use this with a nozzle and a roller, and you can weld small detail work, patches, flashings. It's the most basic type of hot air welder. From there, you could progress to an automatic welder. That's also known as a robot or a machine that moves. So you could put a welder on a long table, on the floor if you're welding extremely large panels. And that pressure and heat come from the machine itself. The next level up after you would go from an automatic welder would be to a stationary welder located in the top right. Very similar to a sewing machine, the welder allows you to weld continuously. So you can weld in this application or on this machine 3D welds, which we'll talk about a lot with hot air welding because it's one type of equipment that allows you to do these curves, do drop stitch, do inflatables, do kayaks, rafts, anything you can think of where it's not just a straight line weld. You can really get into intricate, detailed work with these stationary welders. And even more advanced than, say, a stationary welder like the sewing machine style will be a large traveling head welder or a multiple head welder, where in some instances you'd have derailleurs, unwinders that manage the material through the process to a point where you really only need an operator to start and end the process on an HMI screen. Now, what types of welds can you do? Similar to the other applications, mostly overlap is the largest application, but you can also weld hems, finish the edges of banners per se, or pole pockets where you're putting signs up on street lights or billboards. Heater and pipe welding, enclosing a pipe to go in an extruded track, very common in the tent rental industry. And then, of course, tape welding. Now, what's tape welding? It can come in many different facets. You can weld reinforced webbing to strengthen a structure. You can use it for waterproofing, in essence covering up stitch seams, say, with polyurethane coated apparel, or even acrylic. So acrylics aren't weldable themselves, but using a tape in between the two layers of acrylic can bond those with hot air as well. And to go over some applications so people get a better idea of all these options, we have some photos here to kind of go through those. We have some awnings or some shade structures, water or flood control, oil booms, large billboards covering construction sites, signs and banners. At the bottom is an automatic welder paneling two large pieces together, architecture, so large fabric buildings, inflatables. And I'll mention again, that's a really important part with hot air welding is the option to do really complex 3D shapes. As you can see the picture on the top left there, it's a pretty intricate raft, lots of taping, complex shapes. So that's where you're really going to get into the meat of how hot air can help your operation. And the next picture in the middle on the top is hot air welding for hemming a banner. Billboards is another key part of hot air welding, and also on the bottom, soft-sided trucks. Now that you've learned about the different types of applications, how can this help you? What's my return on investment on a hot air welder? Well, there's a lot of key components, as spoken about in the other technologies as well, are labor costs. How much am I saving? How much faster can I produce these items? Or if you're not producing them at all and you're using a different technology for, say, a consumable product like a tape or glue or thread, how much of that am I going to get rid of and increase in productivity? So on the bottom is an example of welding hems on banners and how much that would save you if you used hot air, for example. Standard size banner, you can see the difference in the speed of production. So you're going almost twice as fast, but in addition to increasing your speed, you're also reducing the cost of a consumable. In this instance, a tape. So you're saving almost $3 for every single one piece of banner you put out and hem with hot air. That concludes the hot air portion of the presentation, and at this point I will turn it back over to Jonathan, and I think we'll start our questions.
All right, thanks, Ken. Looks like we are doing really well on time today, so we've got some time to answer questions. So far, I've got one question coming in from Aaron Collis from Comply Foam, and I'm guessing this is going to go more towards Tracy and Jason, just given the technologies they covered today. It looks like Aaron is interested in equipment that might be able to bond ear seals in hearing protection earmuffs, possibly custom equipment, looking to bond soft and rigid thermoplastic materials. So Tracy, I'll probably have you start off with that, and then Ken and Jason, if there's anything you want to add from your experience, please let me know and we'll do that.
Yeah, sure, no problem. Regarding bonding rigid and soft plastic materials together, it is challenging, and I would say that it's not impossible, but the trick is to actually achieve that optimum melting point between the two different melting points of both the rigid and the soft plastics. My guess would be that an ultrasonic device would be the best, since I know that ultrasonics is used every day in the production of automobile components, very rigid plastics, and to achieve attaching a soft good to this, I would say that would be your best bet, as we've actually developed ways that you could do, for example, a round object completely and do a joining weld. So yeah, it's possible. Probably the best thing to do is to send materials our way. We've got a little test lab here. We'll test out the melting points of each material and together and come up with a recommendation.
All right. Anything, either anybody else, any of the other presenters want to add into that?
I think Tracy covered it pretty well.
Okay. We got another one coming in from Diana. What equipment would be best for small scale 3D seams? Diana, if you want to add any more detail about what you're viewing as small scale, we can add that into that question. But in the meantime, Ken, if you want to discuss a little bit, because I'm guessing hot air is going to be key there. But again, any presenters that want to add, just let us know. Less than a foot is what we're seeing with Diana.
Yeah, typically for hot air, since you're welding through a machine like a sewing machine, most of the products can be as small as a foot, but can obviously be larger, as we are looking at that inflatable earlier. It really depends on when you're dealing with something small, is the desired weld width. So if it's something very small with a lot of curves and stuff that are inside of, I would say, a 2 foot by 2 foot piece, they have a lot of complexity to. On that smaller level, you're probably going to be looking at something more of what Tracy was talking about, a product that, has a certain die with RF welding. And I'll let Tracy talk a little bit about that, since I think based off of the size she's talking, it's probably going to lend itself more in that direction.
Thanks, Ken. Yeah, 3D seams are no problem using RF, and in fact, small seams are even better. I'll reference our experience in the conveyor belt industry, where we're actually welding perpendicular sectionals, or called cleats, onto conveyor belts using 3D tooling. So we can direct the RF. The seam can be less than a millimeter effective seam, and we do this through fairly complex tooling that uses material fixtures and different types of plastic material within the tooling to actually help to hold and form that material as it's being bonded. So the key would be to, again, kind of send us samples of what your end product you'd like it to look like, or a drawing, and then of course the material to be RF welded has to be something in that neighborhood of a PVC or urethane, something to that effect.
And just to clarify on that, in order to use RF welding, I mean, you are going to need a specific tool or die, so that would be something where Diana would need to be looking at a repetitive weld pattern. Is that correct, Tracy?
Yeah, typically. We actually have adjustable tools, though, that can weld a general range of widths, heights, and thicknesses.
Cool. Christina is asking about ETFE welding, and specifically what equipment would be best for long curves with structural elements. So I'm not going to recommend who answers that one. Whoever feels best suited, go for it.
I mean, long curves are usually fine. It's when you get into the tight curves that it becomes particularly challenging, since the process that we use to weld ETFE is a press process. So usually if it's a structure that spans several feet, several hundred feet even, a curve in that end product is not a problem. You basically break it up into small straight welds and turn the material appropriately. So I don't know if that answers your specific question, how long the curve is, and if anyone else has some ideas, let me know.
Or Jason, anything you want to add, or should we move on?
I mean, I would parlay off of what Tracy said. I mean, really, it's just, in all these technologies, it's basically getting our hands on the material and running them through our individual processes of welding, and we would fit, we could look at it and say, this is definitely RF, or this is ultrasonic. These are the directions you need to go. This is hot air. Again, with very limited information, it's hard to fully answer the question. But reach out to any of us or all three of us, and we'll certainly point you in the right direction.
All right. Darcy's asking specifically about Pfeiffer screen mesh. What machine and format for welding is recommended for that?
What is she welding? Is she making shades, or? That's what I would want
Darcy,
to know.
feel free to clarify on that. The question right now says for screen products, such as
screens.
So I'm guessing shade screens.
I'll take over on that too. I would imagine she's going to be putting hems in some pockets to make her screens, and really, you could look at impulse on that to make your pockets. The welding technology that I said, it's a very precise way to weld. It's a very simple way to weld. And say your screen's 9 feet long, you can do it in one hit on an impulse welder. Or say it's a 10-foot weld or a 20-foot weld that you need to put one pocket on. You'll have one hit on it. So I would highly consider looking into impulse welding for that application. Tracy or Ken, feel free.
Yeah, I would agree with you, Jason, on the kind of more standardized size of pocket welding. It is a good resource to basically do the repetitive task of a bar or a hem pocket weld. If and when you need to go to variable lengths, and those lengths do exceed the maximum width of, for example, the impulse welder, it may be a good thing to consider something a little bit more flexible. And that's actually why we created the shuttle process, because we're setting up the material on a table that's out in the open. We're using fixtures and guides to put zippers in or fold the pocket, and then we're moving the material through the machine, and that material actually can be an infinite width in the screen business, or length if you're looking at what the table length is. So it's really up to what your production requires. If it's sizes within a certain limitation, by all means, the impulse is as good a solution as any. If it goes beyond, and you want to have that versatility and flexibility to do the larger sizes, and to actually have less time doing the smaller sizes, then you might want to consider an RF in the format of a shuttle.
So Jason, on an impulse welder, if you've got, let's say, a 9-foot bar, there's no problem welding a much shorter seam on that same long bar. Is it just a longer heat cycle, or can you talk a little bit about that?
Yeah, no, it'd be the same amount of heat cycle. It's just you would put the material in just like you would put it in 9 feet. You can do say I have a 20-foot machine and I want to do a 12-foot or 12-inch hit. That's not an issue at all. Basically, what we would do is I would put a buffer in between the bars. That's it. I mean, literally takes 2 seconds actually to put that buffer down. And in my experience, impulse welding is definitely a home run for shades and precise pockets. And again, the weld size can vary too. You can do 8 millimeters up to 25 millimeters of a weld. So, and again, on Tracy's side of things too, either way you look, I would encourage you to look at both styles of welding, impulse and RF welding. I think both are going to be very advantageous to your company.
All right. While we wait and see if any other questions are coming in. Just to follow up, Darcy's asking if the buffer would just be scrap material there, Jason.
Yes, it would. The buffer would be scrap. Yeah.
So we'll wait to see if any other questions come in. I've got a question for you guys. again, anybody can jump in here. How do users of welding equipment know how strong a weld might be? Do they need to worry about having any sort of testing equipment so they can verify that their welds are good, or can you guys help them in the buying process know what weld results they're going to have and how strong that's going to be?
I'll jump in real quick. The best way to test the strength of a weld is a tensile tester where you're pulling the weld from either side. Oftentimes people will do a peel test. A peel test won't always reveal what strength the weld is, but it actually will reveal how well the weld is across the width of the weld. For example, is it consistent all the way across? So a simple tensile pulling machine, you can go anywhere from a basic homemade one, but there's others out there that actually are a little bit more precise. And then if you peel it away and you see even delamination of the coating, then you've got a consistent weld.
Yep, I would agree with Tracy on that, and we can break it down into even simpler terms. So everybody listening pretty much knows their seam configurations and how strong their seams are. Everybody's hand pulled them, you'll pull in the shear direction. And I would challenge you to send us all your material. Send us, Ken, myself, and Tracy, your material. We'll weld it together with our technologies and we'll send it back to you. And you be the judge. And you'll see how strong that strength is. And I always break it down into, even in the banner world, I would break it down to, imagine you're taking 13-ounce material, 13-ounce laminates or PVCs, and you're fusing another piece of 13-ounce material together. Now you're, in essence, that seam, whether it's a ½ inch, 3/4 of an inch, 2 inches wide of a weld, you're fusing that together. You're making that now 26 ounces. You're doubling that seam strength. There's not single needles. You're not perforating the edges and your overlap seams or your hems, or even with double needle. It's 1 inch, whatever weld width that you have that you choose. It's pretty much standard 1 inch, but the strength of that, you'll notice. I mean, you guys touch this material every day. You work with it every day. You'll know the strength of it. Yes, you can have us tensile test it. We all have tensile test machines and strength test machines that we can give you pounds per foot, to get technical with it. But until you truly feel it and try to pull it apart yourself, that's when you'll know that it's no joke.
I'll add just a little bit more as we're going through the questions here. As far as the strength goes, you will get the required strength you want when welding thermoplastics, because as what Jason said, you're molecularly bonding this and fusing it to become one product. And a lot of times, if it's not for something that is, say, tested for or the government's looking at, if it's just a banner, no, you don't need to necessarily buy a tension tester. Like Tracy was saying, you can do a peel test and get a really good visual if you're getting a good bond, and then pull across it the horizontal way, not the peel way, and that's an even stronger bond. It's really just touching, feeling, seeing for yourself how strong that bond is to get you to see that these are incredibly strong bonds.
All right, thanks, guys. We do have one more question coming in from the attendees. Anthony would like to know if there's RF or high frequency and ultrasonic welders available in portable machines that can be operated on a construction job site for geomembrane welding.
Well, I showed you a picture of the ultrasonic handheld that we have. From a standpoint of bringing it to a job site, it's actually, in theory, an excellent tool. You could put it in a backpack. It weighs less than 10 pounds altogether, so it's a 7-pound generator, and it's a handheld tool. if you were doing repairs, for example, on a job site. The only caveat to that is that in an ultrasonic weld, you need that bottom surface. So you need some sort of hard surface to be underneath the material as you're tacking or repairing a seam. And I don't know if I mentioned it before, but either ultrasonic or RF welds, if previously welded, can actually be re-welded. So that's something good to know. As far as a handheld RF, there's still some development to be done, because usually the traditional generators are fairly large and usually require 3-phase power, although there is single-phase generators out there. What we're really leaning more towards is solid state generator as a way to accomplish a handheld RF weld. And in fact, we have solid state generators that are tabletop generators. That's incorporated into our grommet welder. And so those are a smaller powered but portable. As far as taking them out to the field, there's still a little bit of development to be done on that. But if you want to give me a call later on, we can talk a little bit about it and see if we can adapt our solid state generator welder to your needs.
Christina was asking, just for a repeat on that, Tracy, as far as which welds can be re-welded. You specifically mentioned ultrasonic. Are there any other welds that can be re-welded if there's a failure?
Yes, any RF weld can be re-welded also. I believe, I don't know about impulse, but I know hot air, that's one of the limitations. It's you can't re-weld a hot air weld. But Jason, can you re-weld an impulse weld?
Yeah, you can re-weld an impulse weld too. You can hit it again. But on hot air too, it depends on what's a failed weld. I mean, if it went to the scrim, no, you can't really re-weld that. But if it went to the scrim, it's a pretty solid weld. There are some things, tips and tricks that, Ken and I could definitely show you on hot air welding to fix the weld.
Right, yeah, as Jason was saying, it really depends on if you're asking to re-weld it because you didn't get all the way to temperature, or there was a failure somewhere and you need to repair it, or if you actually destroyed the material down to the scrim, then you've really already destroyed the material to a point where there's no more vinyl on one surface, so you can't really bond back to the scrim anymore. But if there's still the raw material is still there, the vinyl coating, then yes, you can still weld it.
Right. Well, we're just a little bit past the end of the time that was scheduled for this. If anybody's got last-minute questions as I kind of close this out, please go for it. We'll also distribute any of those questions out to the presenters. I would encourage everybody who attended, if you have questions you want to get answered, get in touch with Ken or Tracy or Jason. And, each of them chose a chunk of technology that they were going to present on. That doesn't mean that that's the limit of their knowledge or what they can offer to the industry. So like Jason and others said today, get material in front of people if you really want that, those questions answered. And I think everyone knows that they love to hold things in their hands and experience what can come from that technology. So I want to thank Jason and Ken and Tracy for the time that each of them put into preparing this and just presenting. And thank you to each of you who took the time today to attend. Hopefully it was helpful. We look forward to seeing everybody hopefully at IFAI Expo in just the next month. And just one more reminder, PDF of today's content will be emailed to you. So if there was stuff you wanted to go back and look at as a registered attendee, you will get that. So thanks again to everybody for being involved today, and I truly hope it was helpful to everyone.
Thank you,
Thank
Jonathan.
You all.